Две составные части.
L'île One. L'île One. Okay, so we can start the topology. So next PK is selected for the diagram University of Lille 1, France. He'll talk about Chord diagrams and here.
Okay, thank you for the invitation. So, maybe I begin my talk with a very known fact we have already seen, is that any link in the three sphere can be presented by crossing. Cap and cup. So we have seen this already, and there is a well-known theorem of Virelizier. I think it's 1928, which says that two links are isotopic if and only if their diagrams are related by plane isotopies and so-called Reidemeister moves. So the first one, so the second one, so just and the third one.
Your links are non-oriented.
Yeah. So this is the first one. So there is an oriented version of this. So you have to consider not only this generator, but oriented crossings. So like this one. So this one. So this one, etc. Oriented caps. This one and this one, and oriented cups. So these are cups and these are caps. And this one. Okay, and there is a yes, oriented Reidemeister move. Okay, and also, as we have seen, there is a sort of frame version of node diagrams. So you only consider diagrams so with blackboard framing. And so you have to replace the first Reidemeister move by this one. Okay. So any frame-oriented link may be presented with oriented crossing, cap, and cups. And so that these are generators, and relation are frame Reidemeister moves, the oriented version. Okay. So the main expression is quantum invariant of invariance of links entry manifold. They are defined from so oriented frame links diagrams using some ribbon category. Okay. For example, in the previous talk, the ribbon category in question was a representation of quantum version of Q of G. So, well, I will not explain this construction, but I will come back to this later. But here are two questions. The first question is, so is the presentation of links, so frame-oriented links, by oriented crossing caps and cups, is this presentation is relevant for quantum invariance? In other terms, can we find another presentation of link diagrams which best fit for quantum invariance? And second question we could ask is, do we use all the ribbon category to define quantum invariance? Or does the ribbon category has too much information? Okay. So
in what sense do we use all ribbon?
All the information, of the ribbon category. Does the ribbon category is too much things to define quantum invariant? Okay, so I will address these two questions.
So introduce some weak version of ribbon category.
Yeah, I will say what is needed to define quantum invariance of links entry manifold, and at the end to obtain equalities. So let's take an n-component frame-oriented link. So n-component frame-oriented link. Okay. So we always can see this link as a closure of some specific tangle T here, where T is some kind of tangle which it is a 2M0 tangle, and so the first entries is connected to the second entries with this orientation and so on. So, and I call this kind of tangle n-ribbon tangle. So let's see some example.
Is it the same as bottom tangle?
Yeah, it is similar, same as bottom tangle. Let's do some example as follows. This one. So it is a one-element tangle. This one. This one. Okay. Let's take another. So these are one-element tangle. No, let's take this one. And this one. So these are two element tangles.
Do your rectangles have closed components or not?
No, no.
No closed.
No circle components.
Okay.
It's important. Listen.
Yeah.
And in all your example, you have no cup in your triangle. Is it on purpose or is it just happened random?
No. So a link is
So
a closure of. If you close,
yeah.
there is no cup.
There is no.
This is our example. You can have a cup inside.
Okay. That's what we
Right.
get.
Okay.
And they all have the blackboard framing.
Yeah, this is blackboard one. Okay, so maybe first result. Which is with my Bannoe, one of my collaborators. Okay. So I will say two things. So the first thing, which is the easy part, is that any ribbon tangle is generated by, so I will put some notation. This symbol will denote this ribbon tangle. This one. Okay. Then by this.
So
And
in pictures you should double the number of legs, right? When you go from your symbols to real time.
say it again, please.
Okay.
No. Yeah, you do. This just a symbol for this. And
Generated in what sense?
in the same sense as cup, caps, and this element, so this one, which corresponds to this, and this one, which corresponds to. And last one, which is this one, which corresponds to this tangle. So any ribbon handle can be presented with this generator. And
All the crossings here are just mirror images of the minuses, right?
excuse
I
me,
mean, the pictures of the crossings are just mirror images of the
this is
minuses.
two mirror images.
And the other one here. It's just the whole thing. I mean,
Yeah. Up to, not exactly this one.
It could be the,
Up to something like this. It's the same. Okay. So I will give the relation. So we come back to this maybe later.
I have a question. And you don't need the vertical reflection of the trivalent vertex? You don't need the... You need only like the Chord distribution?
Yeah, I need only this.
Not the other trivalent vertex?
No. So, maybe... let's see an example. So in particular, so consequence of this, so maybe I call of diagrams. So the diagrams in the generator, in the red generator.
So you pronounced the second claim in the theorem, and now you're given a definition.
Yeah. But I will come back to the second later. Yeah.
From my list.
Yeah. So our diagram is a diagram in this generator with no input, with no output. Like diagram B, something like, so let's say plus. Something like this is our diagram. Okay, so the consequence of this is that maybe any link, any fragment oriented link is sometimes the closure of diagram. So maybe I will give an example. So let's take, for example, the trefoil. So trefoil with framing +1. So this surgery of this link will give the Poincare sphere. So this can be right like this. And here, so you need to add two things like this. Okay. So this for framing 1. And so you can see that this is isotopic to this. So there is, you can see it, the isotopic. Let's take this one. And so here, this is a closure of T, and T is represented by, so this, if you cut T, you can see this is plus. So this is this one is negative. This is okay. So this represents the trefoil with framing 1. So this is an example. So this is the first part. Any Riemann tangle can be presented by a off diagram. Okay. So,
So which of them are outputs?
There is no output. No output on the Riemann diagram. There is no output, but some input.
But how can we understand what gross things we are changing to your symbols and what gross
So,
things?
you recover from this diagram the Riemann handle using this operation.
Yes, but vice versa. If I have diagram, how can I obtain your diagram?
Yeah, that's the difficult part, and this is the second assertion of the theorem. So the second assertion of the theorem is the following.
Are you thinking of a ribbon tangle as like a planar algebra or something? Because like you were saying, you're not distinguishing sources and targets. Like in a ribbon category, I would think of like source target information. So you're kind of thinking of it as a planar algebra, right? Or you don't
Maybe,
care?
I don't know. You can define formally as a convolution algebra of some ribbon category, braided category. But maybe we can see this as an algebra. So
Can you have red caps and caps? I think this is a rephrasing of your question, is it?
I think so, yeah.
you have what?
Can you have red caps and caps in your diagram?
No.
Okay.
No.
So it is category, no?
Okay, so the second question, of course, you can present it a link, or more exactly a ribbon handle with such a diagram, but you would like to do this in a canonical way. So to do this, you need to put some relations of diagrams. So if we put relations on off diagrams, so there is a canonical way to associate a ribbon off diagram to a ribbon handle. Okay, what are these relations? So there are several relations. So the first one is that this is like a coproduct, it is co-associative. This is like a co-unit. Okay. So this and this gives you a coalgebra. The second type of relation is plus and minus are convolution inverse to one to each other. So plus minus this plus this. Okay. So there are other relations. So involving the plus and minus with one input, with plus and minus with two inputs, which are, so this one, so plus is something like plus with negative cosine like this. Okay. So other relation of this type. Then there is relation which is naturality of the crossing. So these are relations in this of this type. If I have a crossing and this coproduct, so this is the same as, and so on. And this the same thing for other generators. So of course, so this one is the inverse. And there is a fourth type of relation which corresponds to so this generator satisfies Markov relations for pure braids. So diagram mapping, I have the generators, curve caps, crossings, and relation by the master move. here I consider these generators and these relations. And if we add this relation,
so the last relation is sort of not local. It's you know.
I can write them, but it will take some time. So it's diagram like this one. This is our local. You can do like this. These are local, all are local relations. Okay. 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 So we have other generator relation for frame-oriented links. So now, what is the application of this? So we can construct invariants of frame-oriented links as well. So the first step is to present L as the closure of a ribbon handle. L ribbon L1. And then, okay. So we know now that you can present T by some off diagram, and we have a canonical way to do this. The third thing is to now you represent this of diagram D using a graded coalgebra with varying and twist. So what does it mean? That this generator, you replace it as a coproduct. It's called A. This one by decoding it. This one. So this one by plus or minus with plus or minus twist with plus or minus pairing, and of course this one is the braiding. So if you have an object in a monoidal category and morphines like this, which satisfies the relation I gave for off diagram, you can represent D by this coalgebra. And then the first step, so this way you get, what do you get? You get a morphism from A tensor N to 1. N is a number of components of N. And the first thing is you evaluate with some morphism alpha from 1 to A. And you can define I, the invariant of L with alpha. So this morphism, I call this dA, is dA. the procedure. So maybe let's see the example of the trefoil.
So why does it need to be alpha to the n rather than just an alpha that lives in a dual to the n or a? I mean,
so
why do you need to
this.
use the same alpha in each for each?
Yeah, I could for links I could use different alpha for components, but then for 3 manifold invariant I will. It's better to use one enough. So here I use only one, but you can use one for each component. So okay, so the trefoil with forming 1 can be represented by this of diagram. Now assume you have so your braided coalgebra as before. And you have alpha from 1 to a. So the invariant for this trefoil with alpha. So here, so you replace this generator by pairing plus, then you have the coproduct. Then here you have again the coproduct. Then you have this morphine theta minus, and then you evaluate with alpha. So in other words, this is omega plus delta times theta minus delta alpha. So this is the expression of the invariant associated with A and alpha. So let's see some examples. So, first particular case. So you take C a ribbon category and I take X, so an object of this category. So I can choose A to be X dual tensor X, and alpha associated with X is just the co-evaluation at X and this will give the Rashet-Ekin to RF invariant of N of links colored by X. So, and in particular, you can, if I take C, category C, category representation of OQ SL2, and X is the fundamental representation, we obtain the Jones polynomial. So we can express the Jones polynomial in terms of these generators. And so maybe I can make a remark. So why is this expression easier than the previous one? Because this object has degree 0. And you only use morphism of degree 0. So the co-unit, co-product, and twist and pairing has only between objects of degree 0. That's the simplification. And this makes computation easier. Okay, so maybe I can see a second example.
So, excuse me, what does degree 0 mean for UQSL2? Like in down-to-earth language, does it mean it's a...
So if you have a fusion category, you can always grade the objects in a canonical way. Using, there is a group called the graduator of the category, of the fusion category, and objects have So in this case, QSL2 at root of unity, I think just Z2.
But you didn't need that root of unity for this
Yeah,
variant,
you didn't use unity.
Yeah, you didn't, but this, in some sense, explains which computation are easier using this.
Can I ask, so the multiplication, or like, these would not be degree 0 in the sense that you're talking about, or?
What multiplication?
So you said that presenting a link by these diagrams is kind of simpler than just presenting them by an arbitrary link diagram? Because
I did not use multiplication, just use coproduct.
had you used multiplication somewhere, would that not be degree 0 in a sense?
I have not really time to explain, but maybe I just give the second particular case, and I will come back to your question.
Okay.
So now if I take C, a premodular category, so this is a ribbon category, which is finitely semi-simple and linear, and I denote the simple object by Vi. There is a finite number of simple objects up to isomorphic. So in that case, I can take A is the direct sum of Vi star, so Vi. And I can take alpha to be the sum from I. So the quantum dimension of I, the correlation at Vi. Correlation at Vi, Vi star, Vi.
Premonoidal just means it doesn't have a unit, or
Sorry?
premonoidal means it has no unit for
No, premodular, sorry. Premodular.
Oh,
Sorry. Premodular category. Okay, so in that case, the invariant of L is the Reschettekin Fourier invariant defined with C from surgery from L, or the three manifold obtained by surgery around L. So there is some factor here, but I have no time to explain. So basically, we have this. So you can recover also this way, using this data, the Reschettekin invariant. And to answer your question, this object here, in this case, is of algebra in this category. And this, so we have not only a coproduct but also a product, compatible product. And this is an integral of this of algebra. Okay. Well, so how long do I have? 7 minutes. Okay. Okay, so I have given other generator and other relation of ribbon tangle and links, which is well adapted to define quantum invariant of links and three manifold. And by the way, you do not need to know all the ribbon category to define the invariant, but just the object A with its coproduct, parent, and twist together with alpha. Okay. So
maybe it's an obvious question, but like, do you have examples where you only know part of the ribbon category and you don't know the other part, like for instance graded co-algebras? Is there some nice example that is somehow not a hop out?
yeah, so I have no time to explain.
Okay.
I present you examples which are semi-simple. So, but you can do this using non-semi-simple ribbon categories, and inside there is canonical way to construct such an A. This is a Cohen construction, which is graded of algebra by result of Magid. So there is another example. Okay, so I have talked about quantum invariant of Higgs and three manifold, and another way to present them. So now I will, for the remaining time, I will give some application of this for TQFTs. So, application to TQFTs. Okay. So maybe I will call that three-dimensional TQFT is a symmetric monoidal functor from the category of cobordism, three-dimensional cobordism, to the category of vector space. So what does it mean? If you have a sigma closed surface, then it associates to such a surface K vector space. And if you have a three-dimensional cobordism between two surfaces, sigma 1 and sigma 2, what you get is a linear map between the space associated to the first surface and the space associated to the second surface. Linear map. So this is this association is compatible with gluing of cobordism. This gives you a functor, and monoidal symmetric. What does it mean? It means that for the empty surface, it's just a ground field, and if you have a disjunct union of two cobordism, this is just a tensor product. So you have data like this. Now, example. So if you take C, a modular category, so which is a premodular category with invertible S matrix, so the construction of Reshetikhin-Itorayev gives you a three-dimensional three TQFT. The Reshetikhin-Itorayev invariant extends to a three-dimensional TQFT. So the question is, okay, if we do not assume the invertibility of the S matrix, what happens? If C is only a premodular category, what happens? So maybe I just say the result. So the result is, so you have C, a premodular category. So this is a finitely semi-simple ribbon category. You can consider T inside C, which is transparent, the subcategory of transparent object. This means X such that CYX, CXY is limited to the X transform for all Y. So the binding and its inverse are the same. Okay, so T with restriction of the binding is a symmetric monoidal category. And the result, so with my student Michael Labouche, the following. First, so what you get, so there is TQFT to C, not in value with vector space, but in the category of transparent objects. when C is premodular, so here if C premodular, you can always construct, and using the techniques of diagram, such a TQFT. Now, the second thing is that if C is modular, then this means that T is equivalent to the category of vector spaces, and we recover the Reschettekin-Toreyev invariant. And the third assertion that if C is modularizable, then this means that the category of transparent object, there is a fiber functor from this category to C to vect, fiber functor. And you have that if we compose this TQFT to C with the fiber functor, what we get is a Reschettekin-Toreyev TQFT associated to the modularization of C. Okay. So, if you have a premodular category, you can always construct TQFT, but not with value in vector space, but in value of category of transparent objects, and this generalized Reschettekin-Toreyev construction of TQFT.
More questions?
So there was a vocabulary on bottom tangle, and it seems to be that he has.
Yeah. So the work of Amirov was. So this is related, but not exactly the same. So Amirov. For Amirov, the case was A is. So you have H, it was the case of H is a ribbon of algebra. C is H, and A is H with adjunct action. So with this data, because this universal invariant of links.
I mean the theorem about presentation of bottom tangle if.
Yeah, so he has the same. So the easy part is the same, but he has did not give a relation to give a section, to give a canonical way to have a diagram, a presentation in this generator. That's the main reason. If you impose the relation I gave, you have canonical way to give a word in this generator.
More questions?
Yeah, it seems that this tangle presentation is very you can't extend your things by everything. You can't extend your construction to tangles because the whole construction is you doesn't not relate with the tangle. And so, do you see a way to extend the whole thing to tangles, or is it like this?
No, it is. So what I call ribbon angle or bottom tangle, terminology of Amirov. So it's the same of if you do these procedures, you have T here.
Yeah, you
can see like this.
Yeah, of course.
Like this. And what you get is a n string links. And ribbon angle. And string, so frame oriented. So string link is oriented independently. So it's the same thing as string link. But you cannot extend.
Yeah, there is no way to like compose tangles and or string links.
So here you can compose
right,
string link this way. You get string links. On the side of odd diagram, the corresponding product is convolution product using the product. But extending this to tangle, we do not need this. The question was to define quantum unit, but.
I have a question. Is there a good way to see the invariant of surfaces using the Huff diagrams and so on? So you said this extends to a 3D TQT. Can you? Is that complicated? Sorry.
I can.
Maybe I can just ask you later.
Yeah, I can explain you. If I have half an hour, I can explain. This time is getting great.
Yeah, that's one subject.
Are there more questions? Well, let's try to speak again. I'll step the line from one of these.
One or two?
Two. It's two. From two.
What is
From
an hour?
three.
So we have an hour. We have an hour before lunch. Okay.
If we take a coffee.
Yeah.
C'est un peu le même problème que je suis pas sûr. Regarde,
Oui, donc mais le problème, je sais pas exprimer la string relation avec des diagrammes.
C'est ça le problème. Les ribbons individuels sont nécessaires pour faire
Oui, pour les tangles. Oui, non, mais c'est ce que je veux dire. Tout ça, ribbon de KTS, on fait les diagrammes. On n'a pas besoin de.
Ok, non mais ok.